Hi, I'm Swarupa Sail, course instructor for Fluid Mechanics. In this presentation, we will learn about types of fluid flow. Depending on fluid properties, flow can be either ideal or real flow, and also it can be incompressible and compressible flow. Depending on flow properties, it can be laminar and turbulent flow, steady and unsteady flow, uniform and non-uniform flow, 1, 2 and 3-dimensional flow, and finally rotational and irrotational flow. First one is ideal and real flow. Consider a pipe in which there is a flow of liquid. For ideal flow, there won't be any friction which will be offered by material of the pipe to the liquid. So fluid will be frictionless and viscosity will also be equal to 0, and hence energy loss is 0 for ideal flow. But for real flow, we can see that since there is friction being offered by the material of the pipe onto the liquid, at the point of contact, velocity is 0, and as we move away from the material of the pipe, the effect of friction reduces. And in real flow, friction will be offered and viscosity is considered. Shear stresses occur, causing conversion of mechanical energy into thermal energy. Next is incompressible and compressible flow. Here in this figure, let us consider that there is a liquid in a container and its mass is m and volume is v. After application of load P2, we observe that there is no change in volume of the liquid, and let us also consider that the mass hasn't changed. That means density, which is mass upon volume, is same as that of initial density. So in case of incompressible fluid, there won't be any change in density of the liquid, and the type of flow is referred to as incompressible flow. Whereas in case of compressible fluid, we observe that after application of load P2, there is change in height of the liquid. That means there is change in volume. Since there is change in volume, density also has changed. That means density doesn't remain constant, and hence this type of fluid is referred to as compressible fluid, and the type of flow is compressible flow. Next is laminar and turbulent flow. In case of laminar flow, fluid particles flow in separate layers. So here we can see that the particles are following a definite path. And in case of turbulent flow, fluid particles do not flow in layers. In case of laminar flow, mass mixing between fluid layers does not take place as they are moving in definite path. Whereas in case of turbulent flow, continuous mass mixing between fluid layers takes place. So it is very easy to mix liquids when the flow is turbulent. Friction will be exerted between the fluid layers in case of laminar flow, and in case of turbulent flow, friction will be exerted between fluid and the pipe wall. In case of laminar flow, Reynolds number, which is rho Vd upon mu, is less than 2000, whereas in case of turbulent flow, Reynolds number, that is rho Vd upon mu, is greater than 4000. And if Reynolds number is in between 2000 to 4000, then it is referred to as transitional flow. Here we can see in this figure at upstream section, the flow is laminar. That means the fluid particles are following a definite path. Whereas as it approaches the downstream section, the laminar flow is getting converted into turbulent flow. So this intermediate phase is referred to as transitional flow. And at downstream section, the Reynolds number is greater than 4000 and it is a turbulent flow. The flow has got converted from laminar to turbulent because there is change in height of the flow. Here we can see the velocity distribution in pipe flow. Let us consider this as the wall of the pipe and there is flow of liquid into this pipe. We can see that at the contact velocity is equal to 0 and as we move away from the pipe wall, velocity increases and at the center velocity is maximum. So Vmax represents the maximum velocity. And mean velocity Vm can be calculated by dividing 2 to the maximum velocity. And for turbulent flow, we observe that there is a friction being offered to the liquid till certain length and Vmax is at the center and mean velocity will be equal to 0.8 into Vmax. We can come to know whether the flow is a laminar or turbulent flow by conducting Reynolds experiment, by which we will be able to get Reynolds number. So for finding Reynolds number, we need to know density of liquid, velocity of flow, diameter of the pipe and viscosity of the liquid. So while conducting experiment, the water which is filled in cylinder is allowed to flow through a discharge pipe whose diameter d is known. Later on, water will be allowed to flow into a measuring jar with which we will be able to find its discharge. So discharge divided by area of pipe, that is pi by 4 d square, will give us the value of velocity. The density of the liquid and viscosity of the liquid will be known. So rho Vd upon mu will give us the value of Reynolds number. If Reynolds number, which we get by this equation, is less than 2000, then it is laminar. If it is between 2000 to 4000, then it is transitional. And if it is greater than 4000, then it is turbulent flow. And with this experiment, we can even visually check out whether the flow is laminar, transitional or turbulent. For that, a colored solution, that is potassium permanganate solution, is allowed to flow through the center of the pipe. Initially, when the velocity of the flow is less, which we can regulate using the wall, we find that the flow is laminar. That means we will be able to see a fine straight line at the center of the pipe, which will be due to this colored solution. Later on, when we slightly increase the velocity, the flow tries to get converted into turbulent flow. So the intermediate phase is transitional flow. And once we increase the velocity of the flow becomes turbulent. The colored solution gets diffused into the water. So by visually also we can find out whether the flow is laminar, transitional or turbulent. Next is steady flow. It is the flow in which flow conditions, that is velocity, pressure, density, remain constant with respect to time at a particular section. So here we can see that there is a flow of liquid through a pipe of constant diameter. So constant discharge through pipe is an example for steady flow. And since velocity is not changing with respect to time, we say that change in velocity, that is dou v divided by dou t, is equal to 0. Similarly, change in pressure with respect to time, that is dou P divided by dou T is equal to 0, and change in density, that is dou rho divided by dou T is also equal to 0. And the flow is unsteady flow when the flow conditions vary with respect to time, and this will happen when there will be flow through a pipe of varying diameter. Velocity changes with respect to time. Hence, change in velocity with respect to time, that is dou V by dou T, is not equal to 0. Similarly, other parameters like pressure and density also vary. Hence, we write dou P divided by dou T is not equal to 0, and dou rho divided by dou T is also not equal to 0. Next is uniform flow. It is the flow in which flow conditions like velocity, pressure and density remain constant with respect to space, that is x, y, z, at a certain time, then it is called uniform flow. In case of steady flow, we saw that the flow parameters, if remain constant with respect to time, then it is steady flow. But in case of uniform flow, if the flow parameters remain constant with respect to space, that is x, y, z, then we refer to it as uniform flow. That means change in velocity with respect to space, that is dou V by dou S is equal to 0, and also pressure, that is change in pressure dou P by dou S is equal to 0, and density, that is change in density divided by change in space is also equal to 0. That means dou rho divided by dou S is equal to 0. So we saw that if the change in parameters, that is flow conditions, which are defined by velocity, pressure and density, remain constant with respect to space, then the type of flow is referred to as uniform flow. In case of non-uniform flow, the flow conditions vary with respect to space. Hence, we write the equation change in velocity, that is dou V, divided by change in space, that is dou S, is not equal to 0. Similarly, dou P by dou S is not equal to 0, and dou rho divided by dou S is not equal to 0. And in this figure, let us consider location 1 and location 2. At both the locations, we observe that velocity, temperature and pressure are same, that is V1, T1 and P1 at location 1 is equal to V1, T1, P1 at location 2. Whereas in case of non-uniform flow, we observe that velocity, temperature and pressure at location 2 is different as that of velocity, temperature and pressure at location 1. So at location 1 it is V1, T1, P1, and at location 2 it is V2, T2 and P2. Next we will find out various flow combinations. If flow at constant rate, that means constant discharge Q through a duct, that is pipe of uniform cross section, then it is referred to as steady uniform flow. And if the flow is at constant rate through a pipe of non-uniform cross section, that is tapering pipe, then it is steady non-uniform flow. And if flow is at varying rate through a long straight pipe of uniform cross section, then it is unsteady uniform flow. And finally, if the flow is at varying rate through a pipe of non-uniform cross section, then it is unsteady non-uniform flow. Next, we will define one-dimensional flow. Usually, all the fluids flow along three directions, that is x, y and z directions. So, pressure, velocity and other flow properties vary in all these three directions. But in many cases, greatest changes occur in either along one direction or two directions. Hence, Changes in other direction can be ignored to make analysis much more simple. If flow parameters, that is velocity, pressure, etc. at a given instant of time vary only along the direction of flow and not across the cross section, then it is one-dimensional flow. That means velocity is function of only one coordinate. So that can be written as v is equal to function of x if the flow is along x direction, and v is equal to f of y, it is along y direction, or v is equal to f of z, that means it is along z direction. Here we can see that this is what is the longitudinal section of a rectangular channel which is carrying water to irrigate the fields, and we observe that there is change along only one direction, that is longitudinal section, and there is no change along the cross section of the channel. Hence it is a one-dimensional flow. Next is two-dimensional flow. If flow parameters vary along the direction of flow, that is along x direction, and along one direction, that is along y direction, which is at right angles to this x direction, then it is referred to as two-dimensional flow. That means flow velocity is function of two coordinates, that is x and y. So we can write equation as v is equal to function of xy, or it can be given function of xz, and also it can be a function of y and z. This is the example for flow over a circular section. So when fluid flows over the circular section, there will be change along both x and y direction. Hence it is a two-dimensional flow. And in case of three-dimensional flow, flow parameters vary along all the three directions. That means flow velocity is a function of three coordinates. So we write v is equal to f of x, y and z. Next is rotational and irrotational flow. If fluid particles rotate about their own axis while flowing along the stream, then the flow is called rotational. Here we can see the original position of the particle, and arrows indicate the direction. This is x direction, y direction and z direction. And this is the final position of the particle during the flow of fluid, and we can see that the particle has rotated about its own axis while flowing. Hence it is rotational flow. And if the fluid particle does not rotate about their own axis, then the flow is irrotational. So here this is what is the initial position of the particle, and this is the final position of the fluid particle, and here we can observe that the fluid particle has not rotated about its axis, hence the flow is irrotational. Thank you.